we discussed the features of quantum error correction theory. We described the models of possible errors in the quantum channel, gave a talk on the encoding procedures based on the quantum entanglement phenomena, and considered the scheme for after-error decoding. Now, we have all set to discuss the 3-qubit code, which is analogous to the classical 3-bit code. We know that the qubit channel interaction can lead to one of the 4 possible results. The first situation represents an error-free channel which does not affect the qubit at all. The second situation is a bit flip error, which changes the qubit's 0 state to the state 1 and change the state 1 to a state 0. The third possible situation is a phased error. If a qubit is in the superposition state, then the signs between superposition terms inverse. The fourth situation represents a combined error, which is a bit flip and a phase errors at once. In this case, superposition terms and the signs between them change. Of course, the greater number of errors may occur in the channel as well as their different combinations. But since the error operators are represented by the Pauli matrices, eventually all will reduce to the 4 situations we described. Consider now a 3-qubit code that allows one to protect the qubit in the state psi from bit flip errors. Let the bit flip error probability be p. Then the qubit state can be described by a density matrix which consists of 2 terms. The first term represents a situation when there was no error and the qubit state remains unchanged. It is the projection on the qubit state psi, and it has the probability of 1 minus p, which acts as a multiplier. Since the bit flip error is equivalent to an action of the x logical element, or the sigma 1 Pauli matrix, on the qubit state psi, the second term corresponding to this error can be represented as a projection of the psi on the psi state multiplied by on the left, on the right, and on the right by the x operator, that is the sigma 1 Pauli matrix. It goes with the probability of p. The 3-qubit code that protects the psi qubit from errors of such type is presented on the slide. We see that the code is obtained by the addition of 2 ancilla qubits in 0 states to the qubit psi and further unitary transform. The transform translates a separable system state to a certain entangled state. As a result, we obtain a logical qubit in which every superposition term is represented by a code word instead of Instead of the 0 state vector, we obtain a tensor product of 3 0 state vectors. Similarly, instead of state vector 1, we obtain a tensor product of 3 state vectors 1. The scheme that allows one to perform such an encoding is presented on the slide. It contains 3 input qubits, 2 logical elements in which the psi qubit is a control qubit and one of the ancilla qubit is a target one. Let's see how this scheme works. Suppose the initial state of the qubit is psi, which is equal to alpha 0 plus beta 1. So the total state of the whole system of 3 qubits is then psi multiplied by 0, 0. This can be written in the explicit form and equals alpha 0, 0, 0 plus beta 1, 0, 0. After all our C0 transformations, it turns into a state alpha 0, 0, 0 plus beta 1, 1, 1. Let's take a closer look at these 2 terms. In the first term, the control qubit is in the state 0, and that's why 2 ancilla qubits remain in the state 0. In the second term, the value of the control qubit is 1, and that's why the ancilla bits have their states flipped. Consider now the 3-qubit code for phase errors, which is the action of the Z logical element, that is the sigma 2 Pauli matrix. In this case, the 3-qubit code is formed in the same way. We recall that the action of the Z operator is equivalent to the action of the X operator in the Hadamard basis formed by the plus and minus quantum states. In this case, the action of Z on the state plus gives the state minus, and the action of Z on the state minus gives us the state plus. So, if a phase error occurs in the channel, then on every 3-qubit code's qubit should be translated to the Hadamard basis. It means that the Hadamard transform should be performed via the logical element H. As a result, every 0 state turns to the plus state, and every state 1 turns into the minus state. So, the code word for 0 state will be the tensor product of 3 plus states, and the code word for the state 1 will be the tensor product of 3 minus states. A phase error becomes the bit flip errors, but in the Hadamard basis. The scheme for the bit flip error correction is presented on the slide. So, suppose the initial state of the encoded qubit is the following superposition. Psi-enc equals alpha 000 plus beta 111. After epsilon q, the gate of errors, the value of the first qubit changed, and now our psi-enc is alpha 1000 plus beta 011. Okay, we add 2 ancilla qubits in the state 0, and now our total state of the system of 5 qubits is alpha 10000 plus beta 01100. Okay, and let's now see what our CNOTS element do to the thing. Consider now the first term. Obviously, the first CNOT element will change the value of the first ancilla qubit, since the value of first qubit equals 1. The second CNOT element will actually do nothing because the value of this qubit equals 0, the second qubit. The third CNOT element will flip the value of the second ancilla bit. And again, the fourth CNOT element will do nothing, because the third qubit is in the state 0. And we can now write alpha 10011. The states of ancilla qubits have changed. Okay, let's now look at the second term. Beta 011. And what we got here? The first CNOT won't do anything because the value of the first qubit equals 0. The second CNOT will flip the value of the first ancilla qubit. That's why we have 1 here. The third CNOT will also do nothing because the first qubit was in the 0 state in this term of the superposition. And the last CNOT element will perform the flip on the qubit 2 of ancilla qubits. That's why, by this time, our state is alpha 100 plus beta 0, 1, 1. Actually multiplied by 1, 1. Such a syndrome will lead to the first CC node element, which is here, being triggered only. Now the pair of auxiliary qubits act as the control ones. Since they are equal 1, the first qubit will flip its state, and thus we'll have here 0, 1. And this turns it to alpha 0, 0, 0 plus beta 1, 1, 1. Doesn't it remind you anything? Actually, it is our encoded Psi-enc. And we can see that the initial state is now restored. Actually, these two auxiliary bits are then deleted. That's how the 3-qubit code works. The scheme for the correction of phase errors will be equivalent to the scheme for the correction of bit flip errors we've just considered. It will only have additional Hadamard elements for the change of basis. We won't consider this scheme in detail. Instead of this, let's consider a combined error which is both bit flip and phase errors at once. On the slide you can see the density matrix describing the state of a qubit interacting with the noisy information channel in which both error types occur. Again, the first term corresponds to the absence of errors with the probability of 1 minus p, and the second term corresponds to the combined errors occurrence with the probability of p. It is clear that the 3-qubit code is not enough for such type of errors. However, the same idea could be used for the creation of a code that is resistant to both phase and bit flip errors. This code consists of 9 qubits and it was suggested by Peter Shor, who is already familiar to us. It is the 9-qubit Shor code. Let's take a look at the scheme that creates such a code. As can be seen, at first a phase error qubit code is generated. After that, the 3-qubit code scheme for bit flip errors is applied to every qubit of the phase 3-qubit code. As a result, we obtain a code word formed by the entangled state of 9 qubits, which is resistant to combined errors. We did not prove it here, but you can find some exercises on this theme in the syllabus. So, it was the last lesson in our course. We hope that you enjoyed it and we gave you a better understanding on quantum computations and quantum algorithms. If there are topics you are still not clear with, you can find them in the syllabus where they are considered in more detail. We wish you a good luck. Thank you for watching this course. Goodbye.